We're still talking about contingency tables. In fact, this is the fourth of 5 segments on contingency tables. We had been looking at this as an example, the maternal drinking table, and we had discovered that it had a significance level, that there was a real association between alcohol consumption and malformation at about the 4% significance level. And we got that by doing a Fisher-Exact test, or rather its equivalent Permutation Test, and using the Pearson statistic. But that's not actually the most powerful approach to a table like this. The important thing to recognize in this table is that it is ordinal, not just nominal. What does that mean? That means that the columns are not just random labelings, but have an order that the right-hand column is more extreme than the left-hand column, and in between they monotonically increase. When a table is nominal, that just means the columns have names, and it would have the same significance if you interchanged the order of the columns in any way. But on an ordinal table, the order of the columns matters. The main point now is that we can put this to advantage by choosing a test statistic that actually reflects what our hypothesis is, and that reflects the ordinal nature of the table. So the columns are ordered by an increasing independent variable, and our hypothesis is something like more drinks lead to more abnormalities. Of course, that's not a null hypothesis that we disprove with a p-value test. That's what we hope to discover by disproving some null hypothesis. So the obvious statistic that takes advantage of the ordinal nature of the table is difference in mean number of drinks between the two rows. In other words, when malformation was absent, did the mothers drink less on average than when malformation was present? Now, where did that come from? I just made it up. You're allowed to make up a statistic that you think will be sensitive to disproving your null hypothesis. I'm actually going to carry through 2 examples in this lecture, so I'm going to make up a second statistics. Maybe it's that a small number of drinks doesn't lead to malformations, but that a more extreme number, the ones down at this end of the table, do. And a way to measure that might be to choose as a statistic difference of the mean square number of drinks, so that 0 will still count as 0, 1 will count as 1, but 6 will count as the square of 6, so we'll count 36 times as much. In other words, that will be a weighting of this end of the table to higher values. And later we'll have to discuss whether when I try 2 statistics and carry them both through, I have to do a multiple hypothesis correction. Now once I've made up a statistic, mean difference of number of drinks or mean square difference of number of drinks, I go through and I do the permutation test just as before. In other words, I'm still doing a Fisher-Exact test on this contingency table. The difference is just that I've chosen what I think is going to turn out to be a more appropriate statistic. So let's do the calculation. Here's our table entered into MATLAB, and here it prints out. Here we want to see how many total individuals participated in the study, and this is just a check because this is a number that we've seen before, more than 32,000. And now I need some quantification of what these columns represent. They're not given as exact numbers, they're given as these inequalities or ranges. And I'm going to choose to quantify them by 0 drinks in the 0 column, half a drink in the column that says less than 1, 1.5, this is logical, in the column down here that says 1 to 2. Again, the mid-range here, 3 to 5, I'm going to count as 4. And for greater than 6, I'm going to be conservative and just put the lower bound here. I'm going to put 6. Now you might say, I've lost something here. I don't really know how many drinks each individual drank. I only know how they've been binned here. Doesn't matter. I get to define a statistic, and I'm defining my statistic as having this quantification of the columns of this contingency table. So that's the number of drinks I'm going to impute to each column. Here for my second statistic, I'm going to simply square the values here and get the number of drinks squared in each column. To compute averages from this table up here, I'm going to need to know the total number of events in each of the two rows, and therefore we sum this table over the columns with this statement here. And now let me compute the average number of drinks for each row of the table. We can do that with this matrix multiply. Take the table, which is a table that has 2 rows and 5 columns, and multiply by the transpose of this drinks vector. Then I have to divide by the total number of events in each row, and that is the individual divide by norm here. And I'm going to do the same thing using the drinks squared vector that I computed right here. And let's see what we get out. We get that the average number of drinks in the first row of the table is 0.28, and in the second row, where malformation was present, indeed, the mean number of drinks is higher. Is it statistically significantly higher? That's the question that we're going to answer. And then for square drinks, it's an even more striking effect. We go from 0.26, the mean number of drinks squared, to 0.78 in the second row. Our statistic was not these numbers as a vector, but a single number. A statistic has to be a single number, so it's the difference of these two rows. And a little tricky matrix way of working that out is to left matrix multiply by the vector minus 1, 1 here. Then, in other words, that's the second row minus the first row in both cases. Those differences for the real data come out 0.11 and 0.51. Now the question is, under the permutation test, what does the population of this statistic look like, and therefore what is the p-value for each of these statistics? So we've done this before in the previous segments. We're going to do the permutation test essentially by hand, not by calling some routine in which it's already been encoded. We expand the data set back to a vector, or I should say a little matrix, a matrix with 2 columns and length, number of rows, number of participants in the study, 32,574. We do this by the ndgrid function. We've used this before, but I didn't previously write out how it works. ndgrid gives 2 results. It gives a thing the size of the original table here, that is 2 by 5, that simply labels each cell by its row, and then it gives another one called col, which labels each cell by its column. That allows us to construct this long, skinny matrix D by, for each element in the original table, each of the 10 values down here, concatenating a certain number of rows to the matrix that tell which row and which column in the contingency table that element came from. And we get this long, skinny matrix with 32,000 roughly rows and 2 columns. The check that we always do, just to make sure we haven't bollocksed something up here, is we see whether with the accumulate function we get back the original table. Yes, we do. And now we're ready to, for example, compute the mean number of drinks in the second row of the table. So how do I do that? I'm going to do that now from this long, skinny matrix D. Well, I'm going to pick out the rows of D that have its first column equal to 2, because that means it will be in the second row of the matrix, because remember the first column of D tells what row it's in, and the second column tells what column it's in. Getting a little bit confusing, but you can stop the lecture and go back and think about that. Okay, and then I want to pull out the value here from the second column. That tells what column it's in. And then I want to take drinks, was this vector that I'm addressing of average number of drinks for that element. And so that gives a long vector of how many drinks each participant reported, and I'll take the mean, I should say each participant in the second row reported, and then I take the mean of that. I get 0.39. Well, if you go back and look at the previous slide, you'll see that that's exactly what we got before. So we've done all the manipulations of shape here correctly. Now I want to compute the statistic both for the data and for 1,000 permutations of the data. As before, the idea is to sample from the null hypothesis that there is no association between the row and column variables while keeping the distribution of each single variable unchanged. In other words, keeping all of the column and row marginals unchanged. So we do this by permuting the label. We've seen this before. The difference between the means is going to be this anonymous function into which I plug the long skinny matrix D, and this is this same slightly complicated code before. This is the mean number of drinks in the second row, that's the 2 here, minus the mean number of drinks in the first row of the original table, that's the value 1 here. And we see now when we compute that on the real data, D, we get the same number that we saw before, 0.11. Now we're going to do random permutations. Let's just try one of them first. All we have to do is apply this diff mean function not to the matrix D, the real data as we did here, but to a matrix where we randomly permute the first column of D but leave the second column alone. You could, of course, randomly permute the second column also. It doesn't matter because a random permutation of either column randomizes the association. So we're doing just one permutation here to see if it works, and we get an answer out for the difference of the means. Looks pretty different from for the real data, 0.11 versus 0.014. Okay, but we don't really know until we try it a whole bunch of times. So here with the array function in MATLAB, we apply this 1,000 times, and then we're going to look at, let me call it the p-value because that's what it is. We'll look at the number of these permutations which give a value greater than what we got for the real data here, divided by the total number of the permutations, that's 1,000. And we get a p-value of better than 2%, about 1.5%, as shown here. Let's see what the histogram actually looks like. So the real data gives a statistic difference of mean drinks of 0.11, and that's out here. The distribution under the null hypothesis is this broad distribution here. Kind of ratty looking because we only did 1,000 permutations. And the area under the curve, more extreme than what we actually see, as extreme or more extreme, is this out here, which, as we calculate, is only 1.5% of the total area. So we now have a p-value that's more than twice as significant as when we did it in the previous segment, ignoring the column orderings. That means that we were indeed throwing away useful information in treating the table as a nominal table, and now we're regaining that information and getting a more significant result by recognizing that the table is in fact ordinal. Now for something I'm going to put at the end of this segment, I want to remind you that a p-value is like a false positive rate. In other words, what we're seeing here is that under the null hypothesis, where the mean of the statistic should be around 0, you can see that there's less than a 1.5% chance of getting a false signal as large as the one that we actually see, a false positive, in other words. We're carrying through two tests, so let's go back and do exactly the same analysis for this statistic of squared drinks. So I won't go through the code again. What do we get? We get here a p-value of even better, about 1.1%, almost at the 1% significance level. And the histogram looks like this. The value for the data is 0.51, and that's, let's see, it's probably in this bin here. And the 1.1% of the total area is the area to the right over here. Now I promised you that we have to at least think about the multiple hypothesis correction. We tried two tests. Should we be honest and apply the Bonferroni correction, which is the gold standard, and say that our significance level is twice the best one here, or about 2%? Or shall we say no, the best significance level is what it shows here, about 1%? I think this is the case where you probably don't have to apply Bonferroni. And the reason is mean and mean of squares are highly correlated statistics. And they both turned out significant. So it's not as if we could be accused of shopping for p-values in a uniform distribution until we found a particularly good one. We were looking at two closely related statistics. Both turn out significant, and I think it's reasonable to quote the smaller one about the 1% significance level. On the other hand, if you submitted this to a paper and the referee said you really should apply Bonferroni, you tried two statistics, it would be hard to argue with them, and in this case you would still have a significant result. Unfortunately, I don't know a general principled way to do a Bonferroni-like correction that takes into account that these statistics are highly correlated. It would be good to know such a method. Now here I want to go off on a little bit of a tangent and raise an issue that you might not have thought of. The permutation test kind of looks like you're bootstrap resampling something. You're doing something and then doing something to the data that has a kind of a sampling aspect. It's actually a permutational aspect, and that then you're looking at a distribution of what comes out of that. But I want to explain to you here that the permutation test is not bootstrap resampling. Very fundamentally, the permutation test breaks the causal connection between the two things that you're observing, maternal drinking and malformations, so that we have the null hypothesis that we're sampling repeatedly. Bootstrap resampling is doing, in a sense, the opposite thing. Bootstrap resampling is keeping the connection of each individual data point, but simply resampling from among the data points. And the purpose of that is to tell you how much variation in the signal you might have seen in repeated identical experiments. Now the permutation test is essential in deciding whether the contingency table is statistically significant. That's basically how you do it. Bootstrapping here might possibly be useful in answering a different question, and that question would be, what if there was another experiment that had about the same number of people enrolled but didn't see the effect? In other words, it got what you think is a false negative because you're pretty confident in your positive result. Let's see how you would compute that. Well, now we would compute this difference of the mean statistic. Instead of on the data long skinny vector D, we would choose a random sample of the rows of D, and that's here using the random sample function in MATLAB that we've seen before. So here I'm doing it just once, and I get a statistic value of 0.20. And now with the array function, I do it 1,000 times, and I compute, well, it isn't really a p-value, even though I've named it here p-val, but I'm interested in how often does it occur under resampling that my statistic, difference of number of mean drinks, doesn't even have the expected sign. In other words, gives a value less than 0 here out of the total number of resampled. And the answer is that happens about 8% of the time. Let's see the histogram here. The histogram looks like this. The value for the real data, which is going to be the roughly center of the bootstrap distribution, okay, was up here at about 0.11. And we see that to the left of what I've drawn a red line at 0 here, to the left of here, this contains 78.8% of the data. So what question does this answer? This answers, as I've already said, how often would a repetition of the experiment show an effect with a negative difference of means instead of the observed positive difference of means? Just to nail this difference in the conceptual framework, let me show you the two histograms we've been considering. Here's the permutation test. It's under the null hypothesis, so it's centered around 0, and we're interested in the right tail, which is how often we could have gotten a value as significant as we see for the real data by chance. And the answer was only 1.5% of the time. On the other hand, if other people go off and do similar experiments, 8% of the time, as shown from the bootstrap method, they will not only fail to reproduce the magnitude of our effect up here at about 0.11, but they'll even get the wrong sign of the effect. Both interesting things to know about a contingency table like this one. So let me summarize now both this unit and the one before, in which we've been discussing the Fisher exact test, or equivalently the permutation test. These tests are easy to do. They're done all the time. They're a standard way of reporting significance level for contingency tables. However, if the number of counts in your table are small, as in our little example here that we did in the segment before this one, these tests are less, quote, exact, quote, than they pretend to be, and we've seen there are several reasons for that. First of all, your data will always land in one of these discrete values that the test is capable of producing. And that means that it's always tied with a bunch of other events that land in this bin, and that means that the result that you report is always either over-conservative or under-conservative. That is, if you include this whole bin in the tail area, you're being over-conservative. That's probably the norm and probably the thing to do. But if you don't include it, you're being under-conservative. Some people split the difference and include half the value, half the number of events in this bin when they calculate the p-value. Now, when you do a two-tailed test, the negative of your statistic just lands somewhere here. It doesn't necessarily land on a discrete value of the statistic that can actually be produced by the combinatorics of the data. So it might be, depending on whether this arrow lands a little bit to the left of a significant bin or a little bit to the right of the significant bin, that your two-tailed test might be virtually the same as the one-tailed test, as in the example here, because there's almost no area here. Or it might be quite different from a one-tailed test, kind of the way you expect a two-tailed test to be, having about half the significance, in other words, twice the percentile significance level, if the arrow landed on the wrong side here. In other words, it might be quite different. So what we're seeing here is that this whole construct is fragile to what I call irrelevant number theoretical coincidences about the values of the marginals and how the particular numbers here map into particular values of the statistics here. And what makes that sometimes important is that if you just add one data point to one of these bins, as you might well have gotten in a repetition of the study, or if you use a slightly different statistic from the one that you used, Wald instead of Pearson, or vice versa, it can radically change the tail p-values, especially for a two-tailed test. And we've already seen what the fundamental problem here is. The fundamental problem is we've invented a method that assumes that all the marginals are fixed, while real protocols, we saw a couple of segments ago, don't fix both sets of marginals. Fisher's elegant elimination of the nuisance parameters P and Q is a trap, and it's a trap that we'd actually rather not fall into. So in the next segment, we're going to actually estimate the nuisance parameters, the P's and the Q's. We're going to turn from being pretty much frequentists to being pretty much Bayesians. It's going to make us Bayesians in a p-value world, and that's a little bit of a hybrid. We've already seen that kind of hybrid before when we talked about posterior predictive p-values. That was in a segment on the town family.